I'm Austin Song, and this is my lab report video for Lab 1 charge tapes. The purpose of this lab is to understand fundamentals of charging, electric forces, and Coulomb's law. Through the coding part, we learned to simulate interactions of charged objects in GlowScript, and by collecting our data and applying our formulas, we learned how to use empirical lab data in combination with formulas to determine values for electric force / magnitude of charge on an object. Fundamental principles are Coulomb's law, which is telling us what the electric force is of two charges given their separation distance, and Newton's second law, which is just the base equation for force. Preview of results, tapes were positively charged as seen here when it's attracted to a negatively charged pen. The charge value that we got is 4.26 times 10 to the negative 9 coulombs per tape. Is 2.66 times 10 to the 10 electrons lost per tape, and the ratio of electrons lost to atoms on the surface is 5.1 times 10 to the negative 8. For our observation / data, the system is the two charged tapes, the surroundings is the supports for the upper tape, hands holding the lower tape, surrounding air, all that other stuff. For our measured values, separation when floating was 0.008 meters, tape length was 0.26 meters, and tape width was 0.02 meters. To calculate the result, up here I just wrote out all our measured constants. We're able to set Fg equal to Fe because the upper tape is floating, it's in equilibrium. This is the value for Fg, and we know it's the same as Fe based on that principle. We can assume Qa is equal to Qb because we followed similar charging, like the same charging process. And because we have all these values, we have Fe, K, and separation distance, we can rearrange Coulomb's law to solve for Q. That's what we did here. To find electrons lost, we know that all charge is a multiple of the charge of an electron, so we just divide total charge by charge of an electron to find the number of electrons. To find the number of atoms, we calculate the tape area using our measured dimensions. We're given the dimensions of an atom, so we calculate that area. We divide total area by area of an atom to get the rough number of atoms. And then to find the ratio of electrons lost to atoms on the surface, we just divide the electrons lost that we calculated by total number of atoms we calculated for this value here. Now for the coded simulation, we do pretty much the same thing, just in code. These are all of our constants that are defined. Here we have code that makes spheres to represent the point charges that represent the tapes, just to make a more simple simulation. This is defining force of gravity. This is rearranging Coulomb's law to be in terms of Q. This is assigning equal Q values to each of the tapes. And this is the formula for electric force calculated from the Q, just Coulomb's law. So our outputs are going to be the charge per tape for that separation distance and the electric force. These arrows are just force vectors that make it a bit easier to see what's going on and a bit clearer. These are our results. This is electric force up on the tape. This is gravitational force down. I just also have the electric force vector on the bottom tape to show that the forces are equal and opposite. And these two numerical values are the same as for when we calculate it on paper. For our assumptions, we have to assume that the tapes have equal charge, that they can be represented as a point charge, which goes in line with the fact that the tapes have equal charge distribution. We assume air resistance is negligible, and that the lower tape is parallel to the upper tape. So for our errors, they kind of go in line with the assumptions because the tapes likely were not charged equally, simply because of all the inconsistencies, like microscopic in terms of pull time and speed, all that stuff. Handling the tapes during the process of setting up the experiment caused loss of charge due to grounding through like our hands and all the spare electrons that are just floating around. And the tape was not perfectly flat when mounting it on the stands, so that caused inconsistencies in terms of measuring the separation distance as well. For questions, if electrons had positive charge and protons had negative charge, nothing would actually change. All the observed effects are based on the differences between the two charges. Whether they're positive or negative doesn't really matter. The movement of electrons, if they're positive, the difference still remains the same, regardless of their sign. It's important to handle the charge tapes as little as possible because we don't want excess charge like getting on or leaving the tapes by contacting with other objects. Like in this case, the tapes were positively charged. If we touch them with our hands or touch them to like other objects, it could pull electrons off, which is neutralizing the charge and giving us less accurate data for the total charge on the tape. That's it for my slides. Thank you for watching.